Hey, physics, welcome to another awesome flipped lecture. Today we're going to be wrapping up chapter 8 and talking about friction. So friction you've heard of before, I'm sure, just in casual conversations in life. Friction is the force that opposes motion, and we're going to dive into that today and then wrap up all of chapter 8 into one really cool example that uses everything we've been talking about up to date. So here we go, talking about friction. Friction is the force which opposes motion. It always exists. Anytime something is moving, some of that, the energy that goes into that motion is being absorbed by an opposing force that we call friction. It's always there. It's just, is it there in a little bit, or is it there, in large volumes? Newton said that every action has an equal and opposite reaction, that every force has a opposing force, and we've used the phrase force pairs before, where because this is happening, something else is happening. Friction is part of that opposing force to motion. Okay, so if I sit in my chair and I scoot myself this way, there was some friction in the wheels of the chair that opposed that motion. And if I go back, there you go, some friction absorbs some of that energy too. So generally speaking, in high school level physics or in non-calculus based physics, which is what you're going to be doing here, even if you get college credit for this class. Non-calculus based physics, we like to ignore friction because most of the time it's a very small contributor, but there are some examples where it's a large, it's a large force and we need to deal with it. So you need to be familiar with friction at some level in this course. So friction is both useful and a problem. The only reason that you can walk and you can move forward is because you have some traction on the floor. Your feet, God made your feet with ridges and oils and things like that that grab the ground a little bit, and that friction, that traction, is what allows you to move forward. Think about walking on an icy surface. If you were to try to just walk barefoot across the ice, besides being really cold, you would only take a couple of steps successfully before you fell on your head. And that's because there's much less friction on the ice than normal walking situations. And we like to wear shoes to increase our traction. You wear rock climbing shoes or jogging shoes or running shoes because they have even more friction, more traction than the natural surface of your foot. So we do need friction in order to move around and do things that we like to do. But it can also become a problem. Your motors in your car have lots of things built into them to reduce friction and make friction as small as possible. Lots of lubricants and bushings and oil and things of that nature that help to reduce friction, and then we have to get rid of the heat created by the friction that's still there, which is why we need cooling systems in engines. So friction is a problem. Friction is also a blessing, kind of like in-laws. So friction is proportional to the normal force between two moving objects. And so the heavier something is, the more massive it is, the more it pushes down because of gravity on the surface below it, the more the surface below it pushes up on the object in response. And so that normal force pushing up is proportional to the force of friction. The heavier something is, the more friction it produces as it moves along a surface. And there's also, coming into play what the surfaces are made out of. Again, the example about walking on ice versus walking on like concrete. You have much more friction on concrete. You can walk much easier on the concrete because of the greater traction in your shoes. You change that to your skin versus ice, and the coefficient of friction goes way down. The coefficient of friction is just a measure of how sticky those substances are, basically. How much do they cling to each other as they move past? And we use the lowercase Greek letter mu to represent the coefficient of friction. So the formula for friction is the force of friction is equal to mu, the coefficient, times the normal force. Now this is mu, and if you see this letter and you have to say it, it's the m sound, right? It's the m sound, but it looks kind of like the u, which makes this equation really easy to memorize because friction is fun. F-U-N, that's a mu, but it looks kind of like a U. So friction is fun, and that's an easy way to remember that. F equals mu N, okay? Alrighty, so some pictures here. Here's the example of a polar bear on ice. It's a great picture of a polar bear, probably actually enjoying himself, but we can think of that as there's not enough friction on the ice and he fell down because the traction disappeared beneath his paws. Friction also is useful. We strike matches because of friction, because of the high coefficient of friction between sandpaper and this match head. It builds up heat as we overcome that friction with motion, and the heat lights the match head on fire. So friction here also very useful. Friction and motion. Friction always opposes motion. So if we are pushing backwards with our foot against the ground, the opposing motion is friction, and that goes in the opposite direction. Friction always opposes motion. So if propulsion is up, friction is down. If propulsion is this way, friction is this way. Friction always opposes motion. It's always in the opposite direction. And you can see here a picture that shows why friction is part of the force pair to motion. So if we have an object here that weighs something and we apply a force on it this way, okay, well, part of that force's reaction pair is going to be the normal force. The normal force is going to go up because we're pushing kind of down on the object with this angle, right? There's a component of this angle that is down, and the reaction pair to that will be an increased normal force. And part of this angle, the other component, is going this way, making this object want to slide along a surface, but friction is going to oppose that. So that is the resulting component of the reaction force pair, okay? And here we can look at the fun equation, F equals mu n, and see that the coefficient of friction has to do with how the materials interact with each other. The more that they stick to each other, the higher this coefficient of friction is, and the more the force of friction will be. Alrighty? So, kinetic versus static friction. Objects at rest can absorb a certain amount of energy trying to get them to move before they actually move. And you've experienced this, I'm sure, if you have a heavy object on the ground and you're trying to slide it. Maybe you were moving and you had a box that was heavy. You can push with a certain amount of force before it even starts moving. It'll absorb that force and say, yeah, just kidding, not moving yet. That's the static friction that resists the impulse to move in the first place. Once you overcome that static friction and the object starts moving, now you have kinetic friction, which tends to be a lot less than static friction. So in that example, if you have a big box full of heavy things and you're moving and you're in a carpeted room, let's say, and your dad tells you to slide the box to the door, you push on the box with a certain amount of force and it doesn't go anywhere. You increase the amount of force you push on it, and now all of a sudden the box breaks free and starts to slide, and you find that you can move it a lot easier once it's moving. You can keep it moving a lot easier than you could get it moving. So static friction we can represent as mu sub s. Kinetic friction we can represent as mu sub k. Mu sub k is a constant number. If the thing is in motion, there's always a certain amount of friction. It doesn't change. Mu sub s does change, because if there's no force on the box, on the carpet trying to make the box move, then there's no static friction either. Mu sub s is 0. But mu sub s gets bigger, the force of static friction increases to a maximum value as more force is applied. And when that force overcomes that maximum value, then the box starts to slide, right? So mu can range from 0 to a maximum value depending on the materials. And you'll have to look up what mu sub s and mu sub k are. These aren't things that you will ever be made to memorize. Just look them up, or they'll be given to you in the problem. Okay, so here's a little graph of that. As force on an object goes up, static friction also goes up to a maximum value. Then static friction fails. And as the force continues to go up, then friction goes down and it turns into kinetic friction as the object starts to move. It starts to move here, and kinetic friction, while it's sliding, remains constant. And it is generally much less than the static friction that resisted the motion in the first place. Okay, so with the last situation is rolling friction. Rolling friction is calculated as the difference between the applied force on the wheel, could be because of an engine, for example, and the resulting force of propulsion. And generally this takes into account all of the resistances in an engine or in an axle system or on a bike. Whatever the total resistance is gets expressed as rolling friction. Now there isn't actually a whole lot of friction involved where the wheel hits the road, because that doesn't move. The wheel travels by rotating along the ground, and that rotation hopefully doesn't break loose. This only becomes a factor if the traction fails, if the static friction fails, like if you slam the accelerator down on your car and the wheels break loose before you start to go anywhere, then you've overcome the static friction here. But generally, when we talk about rolling friction, we're not talking about overcoming this force. We're talking about whatever the difference is between the applied force that's trying to make the wheel turn and how much the wheel turns. And so you could talk about resistance in the engine, you could talk about air resistance to the vehicle, you could talk about all kinds of things. But it's simply a sum of the applied force and the friction force. Now, I just used the word difference and sum at the same time. Well, friction is always in the opposite direction as motion. So you are in fact adding these. It's just that friction is going to have a different sign than this force, because these are vectors, remember, and if this is going in this direction and this is going in this direction, they have a different sign. So when you add them, you're going to get a smaller number than this was in the first place. Okay? So let's put all this together, shall we? Let's do one really big scary example and terrify you about chapter 8. No, just kidding. Let's do one of the harder questions you'll see and help you understand that you can conquer this, okay? You can do it. So here is a problem. We have a mass and an ideal string and a pulley and another mass and a 38-degree angle. So steel blocks M1 equals 2.5 kilograms. This is a 2.5 kilogram steel block. And M2 equals 15 kilograms, 15 kilogram steel block. Rest on a horizontal and inclined surfaces as shown. So this is flat, this is inclined. The incline is 38 degrees with the horizontal. The blocks are connected by an ideal string passing over an ideal pulley, meaning we can ignore the mass of the string, we can ignore the mass of the pulley, we can ignore any friction forces involving the string or the pulley. Okay? For this system, mu sub s, the maximum static friction is 0.61. No units in friction, by the way. It's just a coefficient, okay? No units. It's not 0.61 anything. Okay, it's just 0.61. And mu sub k, the kinetic friction is 0.5. If the blocks are initially held at rest, first determine whether the blocks will move and release, and B, if so, calculate the acceleration. So here we have these two blocks. The first thing we need to do is kind of get oriented, right? We need to assign a coordinate system to each block separately and draw free body diagrams. So that's here. Mass sub 1, this guy, is sitting on a level surface, and so his mass, the force of weight on 1, is pushing straight down, and the normal force then is pushing straight up. Here we have the tension, this force that's transmitted to this block because the first one is hanging, right? So the force of tension and then the force of friction resisting that system. Okay, so in this case, friction is a positive direction, tension is a negative direction, weight is negative, normal is positive. Okay, next block is at an angle 38 degrees from the horizontal, which means that this is also 38 degrees, right? So what we have here is the mass of the block going straight down, the weight going straight down, but the weight does not push straight on the surface, which means that the normal force is not just the weight. Here, the normal force and the weight are equal magnitudes, different signs. Here, the weight and the normal force are not equal magnitudes, different signs. The normal force is equal magnitude, different sign of the component of the weight that's actually pushing into the ramp. The component of the weight that goes out of the ramp doesn't matter with regard to the normal force, okay? So here we have a force in this direction going down slope that is the sine theta times the weight. If this is my 38 degrees, this would be the opposite, right? So that's sine, and this is the adjacent, so it's cosine. So here I have weight, cosine theta, which helps me find my normal. Weight sine theta helps me find the force moving it down the ramp. And then I have the tension force here that goes back over to the block. So there's my free body diagrams. Pause the video if you need to and look over those again and make sure that you are oriented for this problem. okay? Now we're going to determine the magnitude of the normal force on each block. So the normal force of block 1 is just its weight. It's the mass times gravity, okay? And so the mass is 2.5 kilograms. That was given to us up here. And the force of gravity is always 9.81 meters per second squared in this book. So these two multiplied together gives me a product of 24.525 newtons. Notice it's positive because the normal force goes up, and in the y-axis, up is positive. So my normal force is 24.525 newtons. Okay. Mass number 2 is similar but different. I don't have just mass, I have the cosine of mass, which helps me find the newtons for my normal force. So my normal force on 2 is the mass times the gravity times the cosine of theta. Again, this is 38 degrees, this is my angle, this is the adjacent arm of the triangle. Adjacent is cosine, okay? So cosine theta, 15 kilograms given to me here. The force of gravity, sorry, the acceleration of gravity times cosine of 38 degrees. Cosine of 38 degrees is 0.78801. Multiply all that nasty together, you get 115.95567 newtons. Way too many digits, but that's okay. Don't round until the end, okay? So this is my normal force on block 2. This is my normal force on block 1. Notice that I oriented my system so that x is parallel to the ramp. And so my system is actually oriented like this. Okay. Now, since any motion of block 2 will correspond with motion, motion in block 1, their static friction can be summed. So I'm only going to do static friction as a sum of the two blocks. I'm not going to solve it independently. Motion must overcome the static friction of both blocks in order to succeed. So the static friction is mu sub s at the maximum value times the normal force. And they gave me the maximum mu sub s as 0.61. So I have the force of static friction is 0.61 times the sum of my normal forces. The sum of the normal forces is this number. Multiply that times the 0.61, the coefficient of static friction at a maximum, and I get 85.693277 newtons. Okay, so the blocks must supply more than 85 newtons-ish of force if they're to move. Do they do that? Now we have to look at this force here and see if it's bigger than the 85.693277 newtons that it takes to make the system move. So I'm going to keep that static force of friction handy over here. All of the x-axis motion will come from the component vector of the block 2's weight parallel to the ramp. So I'm looking at the force of its weight, the component parallel to the ramp. So that's the sine theta. Here's my angle, 38 degrees. This is the opposite side of the triangle. So that's what I'm looking at here. So it's sine theta. Okay. The force in the x direction is its mass times gravity times sine theta. So that's the mass, 15 kilograms, times the acceleration of gravity, times sine theta. Sine theta is 0.61566. Multiply all that together, and my product is negative 90.594586 newtons. Why negative? Why did I say negative, negative, negative? Why did I do that? Well, this is in the x direction, but it's in the negative x direction, right? This would be the positive x direction. So let's make sure that we're keeping all of that together. So the force pulling it down is negative. The force of friction is positive. Force of friction is going this way, right? Okay. So the kinetic force of friction needs to be subtracted. Oh, sorry, here we go. Because this number is bigger than this number, then the block will move, right? The force in the x direction is bigger than the static friction. We overcame the static friction, so it's moving. The kinetic force of friction needs to be subtracted from the force of motion in the x direction to get the net force. So I've got 90 something going this direction. I've got the static force, but now I need to know what's the kinetic force going the other direction, so that I know what the net force is that makes this thing move. So let's solve for my kinetic force of friction. Kinetic force of friction. Fk equals mu k n. Fun. Mu k is 0.50, and they gave that to us right there. So mu sub k times the sum of the normal forces. There's the sum of the normal forces times 0.5. That gives me 70.240335 newtons. Way too many digits. We're not rounding yet. So 70.2 essentially is the resistance to the downward slope. The downward force is giving me 90. The upward force is giving me 70. Downward wins. So it is moving downward, and it's moving downward at the difference between the two. So we're going to sum these vectors. Now remember again, we're summing vectors that are moving in the opposite direction, so they have opposite sign. So even though I'm saying Fx plus Fk, the force in the x direction plus the friction of kinetic motion, even though I am in fact adding these, and this is addition, this is going to come out looking like subtraction because they have a different sign. The force in the x direction is a negative number. The friction, the kinetic friction, is a positive number. So my difference here is negative 20.354251 newtons. Negative 20-ish means that the resulting motion is in this direction. It's negative, okay? The blocks will move in the negative x direction, which is left. With a force of 20.354251 newtons, we can now calculate their acceleration. And again, we're going to consider their masses as one total unit because they're accelerating at the same rate because of this ideal string that's not going to stretch, right? So the net force is the mass of the total system times acceleration. Acceleration is what I want. The F net I just calculated is this negative 20 point yada 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 number equals mass times acceleration, right? Mass is 17.5. If you add 2.5 and 15 together, you get 17.5 kilograms times the acceleration. I'm going to rearrange this equation to solve for A, and that would be the force divided by the mass. And then I'm going to do that calculation. I'm going to get 1.1631006 meters per second squared. Now I can round and correct for significant digits, and I get 1.2 meters per second squared. So it is accelerating down the ramp at an acceleration rate of 1.2 meters per second squared. Wow. Pause the video, go back and look at that enough times so that you understand it and you see what we did. If you have any questions, post them in the comments below, and I will see you tomorrow at class. God bless you. Have a wonderful evening.